Swayam Prabha. Digital India. Educated India.
Today we are going to talk about unitary representations to start with. In fact, by and large we will talk about unitary representations, and then we already know what reducible and irreducible representations are. So what we will do is we will just talk a little bit about a more formal definition of what is a reducible representation, what is an irreducible representation, and that is where we stop today. Now, the logical next step is to derive great orthogonality theorem, which tells us about all the properties of irreducible representations. Okay. So, the problem is if I start deriving this great orthogonality theorem on Friday, I will not finish. So, what we will do is, for the moment we will believe in it. After all, it is written in all these books, Cotton's book, Bishop's book, Atkins' book, all these books. So, for maybe 1.5 weeks we will just take it axiomatically. So far we have not taken anything axiomatically in this course, but we will make a make an exception for great orthogonality theorem just for the time being. So, what I will do is I will just write down great orthogonality theorem, we will discuss what it means, we will talk about the 5 consequences of great orthogonality theorem, and using those we will learn how to construct what are called character tables. That is something that is very easy compared to what we are doing now. Okay. So, let us have something easy in the last class, something that you do not even have to study. So, this is what we have been talking about for the last couple of days. We have been talking about representations, and as we know by now, a representation is a collection of all the transformation matrices for a given basis. When I say all transformation matrices, what do I mean? I mean transformation matrices for all the symmetry operations that are there in the point group that we are talking about, right. And of course, a representation is going to depend upon the basis. I think Rahul asked that question in the last class. So, what basis you choose governs what kind of a representation you get, right. A couple of weeks ago we have gone through some examples where we worked out the matrices and we worked out the representations using different bases. So, today we focus on a particular kind of representation, and that is unitary representation. And what are unitary matrices? A inverse is A dagger. What is A dagger? Adjoint. What is adjoint? Transpose, and then each element is replaced by its complex conjugate. What happens when I multiply an element by its complex conjugate? What do I get? Positive quantity. We are going to need it in a while, so please remember that. Okay. So, as you said correctly, a unitary representation is one in which all the transformation matrices are unitary. A dagger is A inverse. Okay. Why are we even bothered about unitary representations? We are bothered about them because they are very convenient to handle. As more often than not, when you deal with matrices, you will need the inverse. Now, if the transpose is the inverse, or if the adjoint is its inverse, then your life becomes very simple. You do not have to worry about those annoying determinants and stuff like that. Okay. Now, the question that we now ask is it possible to generate unitary representations from other representations? And when you ask that question, the background is already built, because you know that unitary representations or unitary matrices are associated with orthonormal basis functions, right. This is something that we have discussed earlier already, and we had reminded ourselves yesterday as well. When you use an orthonormal basis function, then you get unitary representation, unitary matrices, right. Now the question is, how do I switch? How do I switch to an orthonormal basis? We have gone halfway in answering that question so far. What we have done until yesterday is that we have learned how to switch bases. Orthonormal or not orthonormal, that we have not discussed so far, right. So until yesterday, this is what we have done. We have learned what are equivalent representations. How does one switch bases? One switches bases by using an appropriate what? I switch bases by using an appropriate, fill in the blank, 1 mark question, maybe half a mark question. Matrix will get 1/8. Similarity transformation, right. You switch bases by using similarity transformation. It was even written there. Similarity transformations can switch bases. Okay. Now, so what we did yesterday is that we worked with two different linearly independent basis functions. Did we say they are orthonormal yesterday? No, just linearly independent. We worked with two sets of linearly independent basis functions, the f's and the g's, and the f's and the g's are related by a system of linear equation like this. Fk equal to sum over L equal to 1 to n Alk Gl, right. The only trick here is that we are going down a column, okay, and Gj similarly is sum over I equal to 1 to n Bij Fi. Okay. And then I think we derived this also, that if you take this matrix can be used to perform a similarity transformation that can take you from the F domain to the G domain. What is DGR? It is the transformation matrix corresponding to the symmetry operation R in G basis. What is DFR? It is the transformation matrix of the same symmetry operation R, but this time in F basis, right. By the similarity transformation using A in and A inverse, I can go conveniently from F basis to G basis. That is what we have discussed yesterday. And when we can do that, then we say that this representation consisting of all the DGRs is equivalent to the representation consisting of all the DFRs, right. So, we already learned how to switch bases. So, today what we do is we build upon that and then we try to switch to an orthonormal base, orthonormal basis functions, alright. Okay. Here goes. So, I have kind of laid the spoil sport and given you the answer to start with. Any representation can be seen to be equivalent to a unitary representation through a unitary transformation. I should say through an appropriate unitary transformation, not just any unitary transformation, and we will see what that means. Okay. In other words, you can generate a unitary representation from some other representation by using a proper an appropriate unitary transformation. What is the meaning of appropriate? That is what we will learn today. So, what we will do is we are going to go through this little long derivation, which is not difficult, it is just long, okay. But then since it is long, at the end what we will do is we will write down a recipe of how to go about doing this. But the derivation itself is just and it is a good exercise in remembering what we have discussed earlier also, because we use a lot of things that we discussed a few weeks ago. So, this is a nice topic to discuss before mid-sem. Okay. So, let us start with this. Let us say that we define a matrix H as sum over R dr into dr adjoint. So, what am I doing here? For all the symmetry operations that are there, let us say C3V. What are the symmetry operations? C3, C32, well E, do not forget E, then sigma V1, sigma V2, sigma V3 or sigma VA, sigma VB, sigma VC, whatever way you want to put it. How many symmetry operations? 6. Now, let us say I am working with ammonia. How many atoms? 4. So, I have these 4 atoms N, HA, HB, HC. Using them as basis, let us say I have constructed DE, DC3, DC3 square, D sigma A, D sigma 1, D sigma 2, D sigma 3. So, I have all the DRs, right. Now that I have the DRs, if I have any matrix, I can work out its adjoint, right. So, I have worked out the adjoints also. Now, what I am doing is for E, what is the adjoint of DE? Same unity matrix, right. So, I take DE and I take DE adjoint and multiply them together. Then I take DC3 and its adjoint, multiply them together. DC3 square, its adjoint, multiply them together. D sigma V for each sigma V, its adjoint, multiply together. And then I add up all these products. Okay. When I do that, what should I get? I should get another matrix, right. What should be the dimensionality of the matrix? I am working with a 4-dimensional basis. How will I get a 3 by 3 matrix? 4 by 3, 4 by 4. Whatever is the dimensionality of the basis, dimensionality will be conserved, right. So, this is the matrix, right. H equal to sum over R dr multiplied by adjoint of dr. Now, H is a precious letter, right. We do not write H just for anything, isn't it? It is either enthalpy or it can be Planck's constant or it can be Hamiltonian, right. So, it has to be one of these, otherwise why will I write H? Huh? So, what do you think H is? Is it Planck's constant? Then what could it be? In fact, this was a problem that I think you have worked out in assignment 2. There was a problem in the assignment whereby you had to show that this summation over R dr multiplied by dr adjoint is a Hermitian matrix. So, unless we said that you do not have to work this out, you have worked this out. Okay. So, this is a Hermitian matrix, H for Hermitian. Ring a bell? Has somebody worked this out or not? It is not very difficult to work out. If you have not worked it out, please work it out yourself, fine. But in case you have not worked it out, you have to believe me when I say that I am not about to work that out now. There are too many things have to be worked out anyway. So, that is a Hermitian matrix, alright. So, just believe me in case you have not done it yourself. So, if it is a Hermitian matrix, what is so special about Hermitian matrix, right? So, these are the two interesting properties that are associated with Hermitian matrices. First is that the eigenvalues are real, and second is the eigenvectors that you get are mutually orthogonal. I think we had discussed this, right? We had worked this out. Okay. So, if you are a little rusty on this, just flip back and go to I think that know thy matrices, lecture 5. We must have discussed this in lecture 5. No, 6b, eigenvalues, right, 6b. Okay. So, let me now, knowing all this, write down your familiar eigenvalue equation, matrix eigenvalue equation in that expanded form that we had worked out. I hope you are not completely at a loss when I write this. What is matrix eigenvalue equation? Hx equal to lambda x, right, and what we saw was that there is going to be n number of eigenvectors, correspondingly there is going to be an eigenvalue, right. And then what we did is, these vectors are what, they are column matrices. We said why not combine all the columns and make one square matrix, remember, and then we had constructed a square matrix like this. So, what I show here, instead of writing a x11 and all that, is each of these columns is an eigenvector. Okay. Each column is an eigenvector. Okay. Now, do you remember this equation? We had written H matrix multiplied by capital X matrix equal to capital X multiplied by lambda. What is lambda matrix? Does this ring a bell? Remember this equation? Fine. Now see, what would be the adjoint of this X matrix? Columns become rows and you have to take complex conjugates. So, is everybody okay if I write it like this? Right? Now, since everybody is okay with this, will you agree with me when I say that this adjoint is also the inverse of the same matrix? Work it out. It is convenient if you multiply this matrix by the adjoint. Okay, let this be on the left, let this be on the right. So what is the 1 1 element? This one, what is this color? Blue. So this is blue row complex multiplied by blue column. What should it be? It should be 1. Don't say blue, it should be 1. Yeah. Orthogonal eigenvectors, right? Mutually orthogonal eigenvectors, orthonormal eigenvectors actually. This should be 1. Now the problem comes when you want to see what is 1 2. What will be the 1 2 element? Blue star multiplied by what color is this? Green. I'll believe you. So what should it be? If they are orthogonal, you are multiplying the elements and adding them up, you should get 0. So off diagonal elements are all going to be 0. Okay, what about 2 2? Green star multiplied by green, that is also 1. Okay, what about the last one? What is this color? That is white. So white star multiplied by white, that is 1. So all the diagonal elements become 1, all off diagonal elements become 0. So the adjoint here is the inverse. Okay. So if the adjoint is the inverse, which matrix am I talking about? I am talking about, yeah, of course it is unitary. I am talking about the matrix of eigenvectors, right? So as Rahul has said correctly, the matrix of eigenvectors thus turns out to be unitary, right? Had we discussed this earlier? I don't think so. We have? Okay. Yes. So this is unitary, right? So now what I can do is, next part I definitely remember we discussed earlier. If I now left multiply the left hand side by the adjoint, yes. Then on the left hand side what do I have? I have a similarity transformation. On the right hand side what will happen? You multiply the matrix of eigenvectors by its adjoint, which is also the inverse, you get unit matrix, right? So this is the equation, right? And if we now shed the tomfoolery of colored columns and colored rows and all that, we can write down the equation like this: A equal to U inverse H U. I think earlier we had written, not A, sorry, lambda equal to U inverse H U. Earlier I think we had written lambda equal to X inverse H X, right? Here I want to write U to stress the fact that it is unitary, number 1. Number 2, to be at least somewhat be in line with Bishop's notation. Okay. So if I read this and if I try to speak this, say this in English, what will I say? The lambda matrix is obtained by a unitary transformation of the Hermitian matrix. right. The matrix which has the eigenvalues of the Hermitian matrix along the diagonal and 0 everywhere else is obtained by a unitary transformation of the Hermitian matrix. Okay. But while we say this, please do not forget that this is not just any unitary matrix, it is a particular unitary matrix. Which matrix is that? It is a matrix of the eigenvectors. Okay, so far so good. Any question? If not, let us clean this up a little bit. This is what we will need, right? H is a Hermitian matrix. Better write this down, because the thing is, at one point we are going to erase this also. There is only so much you can write on a slide, right? But we will need this, and it is very easy to forget what we are saying now in the maze that we get into after this. So please write down that H equal to sum over R dr multiplied by dr adjoint, that is one, and second is lambda equal to U inverse H U. We are going to need this later on. Of course, you are all masters of manipulation, you know how to take square of whole sides, then transpose and take cube root and get the answer. That is basically what we are trying to do after this. Please write this. Okay. Can we go ahead now? Lambda equal to U inverse H U. Okay. So now, let us now talk about two equivalent matrices, dr and d prime r. Dr is any transformation matrix that you get. You have used some basis without bothering about whether they are orthonormal or not, right. You have used some basis and you have got the transformation matrices. Using the transformation matrices, you have built the representation. So dr is that kind of a transformation matrix, right. Dr is a transformation, an innocent transformation matrix. We do not bother about what the basis is. We have just used some basis that we like and we have got dr, we know nothing more, alright. D prime r is a little less innocent, because d prime r is obtained by the similarity transformation of dr, right. Of course, anybody can call my bluff at this point and say that dr is also it is also possible to get dr by a unitary similarity transformation of d prime r. That is right, but what we are saying is that we start with dr, perform a similarity transformation and get d prime r. And if you notice, we are performing the similarity transformation with a particular unitary matrix. Which matrix is that? It is the matrix of the eigenvalues of H. Eigenvectors, not eigenvalues, sorry. It is the matrix of eigenvectors of the H matrix. Okay. What is H matrix? This is how you get H matrix. So, see, everything is correlated. Okay, please, it's important to understand here that we are not really taking arbitrary matrices and multiplying left, right and center. Okay. You start with dr, alright. If you perform a similarity transformation, you are going to get d prime r. On the other hand, if you take all the drs and their adjoints, multiply and sum over all the symmetry operations, then you generate a matrix H. From that, you can get the matrix of eigenvectors U. D prime r is the similarity transform of dr using this matrix of eigenvectors. Okay. So, there is a correlation. It is not as if D prime, H are all uncorrelated, scattered, no, everything is correlated, alright. We will come back to this, but this also please take down lest we forget later on. D prime r equal to U inverse dr U. Okay. So, our basic first matrix is dr. Will you believe me if I write this? The adjoint of d prime r is the similarity transformation of the adjoint of dr. Yes.
U is the matrix of eigenvectors of
H.
Is U diagonal matrix?
U cannot be diagonal matrix, right. lambda is diagonal matrix. I mean, I should not say that it cannot be diagonal matrix, but in the most general case it isn't, it is not, alright. So, adjoint of d prime R is also a similar similarity transformation of the adjoint of dr. Okay, so far so good. Now, with this what we do is we can start playing. What do? I know what H is. H is sum over R dr dagger. So, what I can do is I can take this definition and substitute there, right. This is what it is. So, I might as well expand H in the definition of lambda. Okay, you see where we are going. We are going a long way, but the destination is interesting. So, this is what we write, lambda equal to sum over R u inverse dr dagger u. What can we do next? What should I do next? Replace by what? By which equation? Well, eventually we will do that also, but then see the second equation relates dr dagger with d prime r dagger. Okay. What we can try to do is this, we have to get to d prime r, of course. So, we need to convert this into a product of similarity transformations. So, here you see dr is left multiplied by u inverse, dr dagger is right multiplied by u. So, you can put in E, and E can be obtained in many different ways. So, this time we choose to obtain E by writing u inverse, right. U inverse. So, if this was u and this was u inverse, we would have written it as u inverse u, no problem. Okay. So, when I write that, what do I get? U inverse dr u inverse dr dagger u, right. The first one is a similarity transformation. What does it give me? It gives me d prime r, d prime r. Second one is also a similarity transformation, d prime r dagger. Okay. So, nice, I can write this, and what I can do is if I sum this up over r, then I get lambda, right. So, here what we did is that we just wrote the terms. Now, if you sum it over r, then you get lambda once again. Okay. What do I do next? Let me see what a diagonal element is to start with. You remember lambda is a diagonal matrix, right. See, this is what the diagonal element is going to be. Lambda jj will be once again sum over r, sum over j d ij prime r multiplied by dji prime r dagger. Is that correct? Let us see what is lambda 1 1. Lambda 1 1. What is lambda 1 1? d11 prime r multiplied by d11 prime r dagger plus d12 prime r or d21 prime r, d12 prime r, right. So, the summation is on j, the second one, d12 prime r multiplied by d21 prime a dagger, summation is on j. So, j is the first element here, and so on and so forth. You sum j equal to 1 to n. Is that, are we all comfortable with this? It is a diagonal element. I don't care about off diagonal elements because I know already that diagonal element off diagonal elements are all 0, right. I only care about the diagonal elements. What are the diagonal elements? Are they all 1? Then what are they? The lambda values, right, the eigen values. So what are the eigen values? They are all real, right. Why? Hermitian. Hermitian. Are they all positive? I don't know. Maybe, may not be. Probability is 50%, since we don't know anything else. Okay, but they are real numbers. That much is sure. Okay. So are we all okay with this notation? Sum over j dji prime r multiplied by dji prime r dagger. Okay with this?